Hello! Time to answer some questions. So, in December, on Mondays from 2 to 4 p.m. Eastern Standard Time, I am teaching an office hours class.
What's an office hours class?
Dang it, I had perfect hair. Office hours class. Basically, it's like office hours, but it's virtual. So I am allowing up to 7 students to take the office hours class, and we all meet in Zoom, and then we just take turns asking questions. And the cool thing about that and doing it together is you get to learn from other people's questions too. And so to give you kind of a preview of what that looks like, I'm going to answer some questions posted on YouTube. Why not? That'll be fun. With the caveat that usually when somebody asks me a question, I almost always respond with a question in return just to make sure I understand the question. And I can't do that here. So I'm going to do my best to try to interpret what you're trying to ask me. And the other thing that I like to do when students ask me a question, especially if it's like an advanced question and I have several beginners in the class, I will give an overview of how this question fits into like the broader field of statistics. So let's try that and see how it goes. All right, this question is from Trini RT6XN. I have a question. I've noticed. I've Googled for it, but it's not crystal clear to me. What is meant by control for example, class size here? So I am understanding it means to make that thing or variable we're controlling for constant, kind of, ish. But how is that presented in a model? And would the value of the column class size just have a single value in the entire data set? No, that's not how controlling works. Okay, a better way to think about it, and I think I posted a video about this once to talk about what the idea of controlling is, or holding things constant, or whatever. So the basic idea is that theoretically, let's say that you are interested in the relationship between, I think in my textbook I use the example, success in a career. So maybe we'll measure that by wealth based on how hard you work. And I'm not going to worry about how that's measured. Let's just say that we've got some measure of hard work. But you're worried that there might be a confound there, that socioeconomic status might play a role, or parental income or something like that. Let's say parental income. And so you want to establish, or you want to identify the strength of the relationship between how hard you work and how much you make, but you worry that parental income is going to influence that relationship. So what do? One approach is to hold constant. And theoretically what that means is that you find a bunch of people whose parents made the exact same amount of money. So let's say you find parents who made, on average, $75,000 a year. So what you would do is you would gather all those people whose parents made $75,000 a year, and then you would measure the relationship between, what are the other variables? Hard work and income. And if there's still a relationship, you would say, hey, we held that constant. Or in this specific example, everybody had the same score. So that's where the idea holding constant kind of comes from, is that theoretically everybody has the same score. And of course, you wouldn't do that just for parents who make $75,000. You'd also do it for parents who make $85,000, $100,000, whatever. Now, in reality, what we do in statistical models is we don't actually do that. It theoretically does that. So it's more a theoretical idea. You're not actually making things constant. You are theoretically saying, all right, is this relationship still there if I look at a constant value of this covariate that I'm looking at? And I'll go ahead and link the video that I was talking about, because there's I think if I remember right, I explained 3 different ways to think about what holding constant means. And so if you want more information, check that out. Question number 2 comes from Only Here Alone. Only Here Alone. Sounds very sad. Do you need a hug? There. A hug from Quant Psych Dude. All right, I have 2 questions. Although I think this applies to Poisson family of models, would you say checking for overdispersion falls under such needless tests also? Okay, so I believe this was in reference to a video that I made about how testing for normality is useless. And so is testing for linearity, and so is testing for heteroscedasticity and all those things. And so basically, big picture stuff here. So big picture, we have models. We fit models to data. And very often, if not just about always, well, very often we make assumptions about the model, that this model is only appropriate if the following conditions are met. And then historically, what statisticians recommended was that we test for these assumptions. So if we assume normality, we do a hypothesis test to try to see if we could reject the idea that the data are normally distributed. And that's actually a stupid way of doing things. If you want to know why, I'll reference that video. So now this person is talking about what's called a generalized linear model. So there is a type of model called a Poisson model, and Poisson models are there to model count data. So maybe you do the number of times somebody works out in a given week. So you're going to have a bunch of people at 0, a bunch of people at 1, a bunch of people at 2, et cetera, et cetera. And so it's very unlikely that that these data are going to be normally distributed. And so you can't use a normal distribution model. You instead have to use what's called a Poisson distribution, which allows for data to be skewed. So that's the basic idea behind a Poisson model, is that you are modeling count data. Now, one of the assumptions of a Poisson model is that the mean is equal to the variance. So normally in a normal distribution, you have two parameters. You have the mean and the spread, or the standard deviation, or the variance, whatever. Whereas a Poisson model, if you have count data, it's very often that the mean actually equals the variance. Or maybe it could be the standard deviation, I can't remember which. And so if you are going to fit a Poisson regression model, it's going to assume that your mean is equal to your variance. Well, what if it's not? And that does happen. What do you do then? So this person is asking, do you need to do a test? And and we call that over dispersion, by the way. If your mean is not equal to your variance, usually what it means is that the observed variance is higher than the mean, or it's a larger value than the mean. And so we call that over dispersion, or in other words, it's dispersed over like too much, I guess. So do you check for over dispersion? So I guess I don't know if this person is asking, does it make sense to do a hypothesis test for over dispersion? In which case I would say no. And then the second question is, and then or the other way that I could interpret that is, should we check for over dispersion? And I would say absolutely. And I would say the same thing about normality. You should check for normality, just don't use a hypothesis test to do it. You would use visuals, for example. Or you could use a sensitivity analysis. And I would say the same thing here, that if you're worried about over dispersion, then fit a Poisson model, and then fit a negative binomial, which is exactly like a Poisson, except it allows for a different parameter for the dispersion parameter, and see if the two models give you different results. If they don't, then it doesn't matter. Just go with the Poisson model. If they do give you different results, then go with the over dispersed model, or the negative binomial. So hopefully that answers that question. Number 2, more importantly and generally, I believe your statistical doctrines, as I've learned a lot from you about generalized linear models. Been using mixed models too, but the problem is that I can't cite a YouTube video, especially when a reviewer who doesn't belong to the same school of thought challenges me as your statistical disciple. Statistical disciple. I usually call my students Padawans, but I'll take disciple. That works too. Could you please include pivotal references that could be cited for these concepts, and if not available, are you doing anything to make your school of thought represented in literature? Very good question. So, yeah, that could be hard, because a lot of things I just say off the cuff, like, by the way, here's what we know. And I might say like dozens of those things and not think of a citation. The best thing that you could do for citing me would be my textbook, as well as my papers. And if I say something that is definitely and that's another thing, that some of the things that I say aren't Dustinisms, if that makes sense. I don't know that it would make sense to cite me because it's something that other people have said, and I'm just kind of regurgitating that information. But I will do my best in the future to, if I make especially a claim that is not widely known, I will do my best to cite something. So that's not really a information question, just anyway. So that's the answer to your second question. Yes, I will try. All right. Anna V2295 says, hello, Prof. Fife. Hello. Good to see you. I'm very curious about what kinds of models / methodologies / tests come to mind for you for a study that investigates the differences in fertility responses to the COVID-19 pandemic across socioeconomic status groups. It would be incredibly awesome if you could compare your insights as an expert with what I had in mind for my study thesis. Okay, so let me read this again. Investigates the differences in fertility responses to the COVID-19 pandemic across socioeconomic status groups. So this would be a point where I would want to ask questions. So it sounds like the outcome variable is fertility responses. My first question is, how are you measuring that? I'm not exactly sure how that's measured. I've never had fertility treatment for obvious reasons. I do have a friend who did an egg retrieval, and through that process, she had to have the hormonal injections. And at the end of the day, one thing that you could measure is the number of eggs retrieved, maybe. The number of viable eggs retrieved. So maybe that would be your outcome variable, in which case you might be looking at a Poisson distribution. And so you're looking at fertility responses to the COVID-19 pandemic. So when I see 2, I think you're trying to build a prediction model predicting fertility responses from pandemic. So to me, that seems to suggest that you have a bunch of participants who had fertility treatment during the pandemic and a bunch that had fertility treatment before or after the pandemic. So I don't know if that's what you mean, or if you're trying to say all these people were during the pandemic, in which case it's not a variable and you can't model it. But instead you could just say this is a kind of subpopulation that I'm just looking at fertility responsiveness during the pandemic, if that makes sense. And then across socioeconomic status groups. Okay, so I think the primary research question is, how does socioeconomic status affect fertility responsiveness? And so again, assuming, a lot of assumptions here because I don't know, assuming fertility responsiveness is measured in the number of eggs retrieved, then you could do a Poisson model, predicting that, just a very simple Poisson model, predicting that from socioeconomic status. And I also don't know how that is measured. Is that a continuous variable? Or is that just measured by annual income? In which case, but it says groups. So maybe people have been classified into different groups. So let me say one comment on that. If you have, if you ask participants their income, and then you classify them as low, medium, and high, don't do that. Instead, use what their response was, their actual income. So I hope there's no sort of artificial dichotomization or trichotomization or whatever's beyond that, artificially creating a categorical variable from a continuous variable. But let's say that you do have established groups, that here's high, low, medium, whatever. So yeah, you just do a Poisson model, and you end up estimating the differences between the 3 groups, and that's pretty easy to do. And if COVID-19 is a variable, then you could compare COVID versus non-COVID. What's not clear to me at this point is what your exact research question is, because if you do have these 2 variables, that leads to several different research questions. You could be asking, what is the effect of COVID controlling for socioeconomic status? Or you could ask, what is the effect of socioeconomic status controlling for COVID? Or you could ask, how does COVID affect different socioeconomic status groups differently in fertility? So you're looking at an interaction. Or it could be a model where you're saying, which one of these 2 is a bigger predictor of fertility responsiveness? The presence of the pandemic or socioeconomic status groups? In which case you're basically looking at both main effects and seeing which one of those is bigger. So it really depends on exactly what you mean. So yeah, try to, if you are watching this video, go ahead and that goes for everybody. If I misunderstood something, you're welcome to write a comment and then I can respond to that. So anyway, that would be my response. Good luck on your thesis. All right. Yashagrahari. Don't know if I pronounced that right. Cool name though. Hey, I have a nominal categorical variable, say with 10 groups. Yikes, that's a lot of groups. And a continuous variable with data size 150. I'm assuming data size meaning sample size. And find it difficult to calculate the relationship between the 2. Can you please help suggesting any method to get a metric of association between the 2 variables? A metric of association. That's interesting. Metric of association. So there's something called a polychoric and a tetrachoric correlation. Polychoric correlation. In statistics, I'm just reading like a Wikipedia summary. In statistics, wow, that's a mouthful. In statistics, polychoric correlation is a technique for estimating the correlation between two hypothesized normally distributed continuous variables from two observed ordinal variables. Okay, so that doesn't work. So basically that's saying if you've got two continuous variables that have been basically trichotomized or something like that, categorized. So you have two categorical variables. So that would be a polychoric correlation. Tetrachoric, I think, is something similar. Tetrachoric, to measure rater agreement for binary data. Okay, so that would be like polychoric, except one of the variables, I believe, is continuous. One of the variables is categorical, so that's not going to help. Okay, so actually, ha! I got a good answer. I've got a good answer for that. So, okay, let me say a couple things first. So the reason why I'm struggling with this is because, like, if you have a binary predictor variable, that's easy. You could just calculate the mean difference. But when you have 10 different groups, there's a lot of mean differences. Group 1 versus group 2, 1 versus 3, 1 versus 4, 1 versus 5, etc. And then 2 versus 3, 2 versus 4, 2 versus blah, 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 blah. And I think it ends up being 10 times 9 divided by 2, 90, 45 different comparisons. I believe that's a formula, maybe. Lots of different comparisons you can make. And so that's kind of where my mind started going at first. And with 10 groups, that's going to be hard. And how do you like aggregate that into like a single measure of association? And I couldn't think of a way to do that. But then I thought, oh, hey, I'm smart. I thought of something else. It's late, sorry. What you can do is you could build a model comparison. Like, say you're in R, you would build, and let's say your categorical variable with 10 different groups is called A, and your outcome is called Y. So you'd build a linear model, Y tilde A, that's your full model. You would build a full model with Y tilde A, with just your group predictor, and then a second model with Y tilde 1. What does that mean? That 1 means just fit an intercept, which is equivalent to saying just estimate the mean of Y. So you're comparing a model where you have the mean of Y versus a model where each group has their own mean. And then what you could do is you could do model.comparison function with flexplot, and that will estimate AIC, BIC, Bayes factor, those sorts of things. And all those are, in a way, a model of association, or a metric of association, but you also get an R squared, which is exactly a metric of association. And and I've actually done this, I can't remember when I did this. If you want to have like a correlation-like coefficient, what you could do is you could take the square root of that R squared. Because R, the correlation, squared is equal to R squared. And so let's say you explain 50% of the variance. So R squared is equal to 0.5. You could say that your correlation between this grouping variable and the outcome is 0.25, because that's the square root of 0.5. So hey, look at that. I came up with an answer. Hopefully that helps. But I would also recommend like plotting it and looking at the mean differences and that sort of thing. But that'll give you like an overall summary of, all right, among all these groups, on average, group membership helps us explain this much of the variance, which is an association. And the next question is by Trash Flora. There's got to be an interesting story behind that name. If you're here, comment. I want to hear it. Your video is very clear. Cool. Thank you. Can random effects be continuous data? Absolutely. So, all right, got to keep remembering to step back. So normally we fit models to data. That's the whole point of statistics. Normally we make the assumption that each of our data points are independent, but sometimes you do what's called a repeated measures, where you measure people repeatedly, in which case the data points are no longer independent, so you can't use standard statistical procedures. So instead what you use is what's called a mixed model. And the same things could happen if you have clustering, like if you have a bunch of students taught by the same instructor, then their responses aren't going to be independent. They're probably going to be correlated. So anyway, in these situations, you would use a mixed model, which basically, not exactly, but kind of sort of, what that means is that for each of these groups, so let's say we are talking about classroom, for each classroom, it fits a regression line for just that classroom. And then it does it for another classroom, and then it does it for another classroom. And then at the end of the day, it aggregates them. And then I'm totally oversimplifying things, but that's essentially what happens. So this person is asking, can random effects be continuous data? So random effects means that each of those clusters has their own regression line. And so what this person is saying is, can random effects be continuous data? Or in other words, if you have a continuous predictor, so let's say, using that same example, we got students. They're all taking a class together, so their responses are correlated. And maybe you want to look at GPA at the end of the semester as a function of parental income. We're using that a lot today, I guess. So each child's parent has their own income, and so you want to look at the relationship between how wealthy their parents are and how well they do at the end of the semester measured by GPA. So can random effects be continuous? Yeah, absolutely. In fact, more often than not, continuous variables are more likely to be random than categorical variables as a predictor. I assume that's what you mean here. Can random effects be used for continuous predictors? Absolutely, yes. In fact, that's, I guess in my mind, that's the default, that if you have a continuous predictor, then you're going to model it as a random effect. So, and then I could have used this person's example. I was thinking GPS, X and Y values, 2 separate columns, as a random effect for the response variable, sick pigs and healthy pigs under some environmental explanatory variables. Okay, so you're using GPS as a predictor for a binary variable, whether the pigs are sick or healthy. Okay, under some environmental explanatory variable. So I'm not quite yet seeing where the mixed models need is coming from. I'm assuming these are a bunch of pigs who are in a what do you call a group of pigs? I'm going to totally Google that. What do you call a group of pigs? A passel or a team, apparently. Or a litter. But that's only applicable to piglets. So, okay. We'll call it a passel because that's the most fun one. So you've got different passels of pigs. Actually, I'm not going to use that because I'm going to forget what passel means. So you've got different colonies. I'll call them colonies. You've got a colony of pigs here, and you want to control for the fact that, of course, if pigs are sharing a colony and one gets sick, you're more likely to get the other people sick. So I'm assuming that's why you're using mixed models. So now the person is asking, can you use GPS as a random effect? Yes, you can. I don't think it's a good idea, but you can. And why don't I think it's a good idea? So GPS is really a stand-in for geographic region. And so I guess here's my problem with GPS is if you think about like income, the higher the value of income, the more money you're making. It's what we call a monotonic relationship, which means as you go higher, it's always higher than the last value. Whereas with GPS, let's say you're looking at the Y value, north and south, it's not monotonic. As far, well, in my mind, I'm thinking, okay, why would you want region? You would want it because of the weather. And let's just say temperature as a substitute for weather. As you go further north from the equator, it generally, but not always, gets warmer. But then as you go south, did I say it gets warmer? It gets colder the further north you go. And it gets colder the further south you go. So it's not a monotonic relationship. So adding that as a predictor, I don't think is going to be very helpful. And likewise for what? Like what happens as you go around the equator? That's the word. Nothing. So if you're interested in temperature, why not just use temperature as a predictor or some other function of climate, like how much average rainfall they get a year or something like that. Basically, I don't see anything about GPS, the values of the GPS that is particularly helpful for predicting whether pigs get sick or not. So I just think about what you are using GPS as a substitute for, and try to find a better measure of that so that it's monotonic. So, yeah, hopefully that helps. But to answer your real question, yeah, with continuous data, absolutely. You can use it as a random effect, and more often than not, you are, probably. Or at least more often than you would with a categorical variable. All right. Parthosin, 5942. Hey, quick question. If it's bad practice to dichotomize continuous variables, yes, it is. Then how does one estimate, say, for example, the effect of weather shocks on agricultural produce? This is something I've been working on, where I take within entity deviations from the long run average and then dichotomize it based on an officially documented cutoff. But if there is no cutoff, how do I define what is a shock in my case? So I don't I don't have enough context to answer this confidently. But I think what you're asking is, all right, weather shocks. You want to know, like, if something abnormal happens in the weather, can you dichotomize it? And that really depends on how you're talking about that. So let's say, for example, I know that if you are planting a garden and you plant it before the last frost occurs, a lot of those plants do not do well when they have frost. And so in this case, is it okay to categorize temperature as a stand-in for weather shocks? And I would say, knowing what I know about gardening, which isn't a lot, but it's some, that may be okay, just because there is something that physiologically, I don't know if that's the right word, there's something that physiologically happens to the plants, that when water freezes, that something biological happens within the plants that really has a strain, and then that specific threshold is important. So, but that's not like an arbitrary cutoff. That is the point of freezing, which if water freezes within a plant, that's damaging to it. So in that case, maybe a cutoff makes sense, but I'd still rather use temperature itself as the continuous variable instead of just doing the cutoff. So, yeah, I don't have enough context to answer this confidently, but I would say that my intuition says that whatever they designate as a cultural shock is going to be based on continuous data, so why not use the continuous data instead? So that would be my answer. Having said that, I think this actually, I might use this example again in the future. Dichotomizing, did it freeze versus not? There's some merit to that. And that would be interesting to do a study on that, and like a statistical study, and say, how much does it change your conclusions when you analyze temperature, especially if it's on a Fahrenheit scale where like 32 degrees is super arbitrary. Like, why is 32 degrees the freezing point? Stupid imperial system. But, and so I don't know what I'm saying. It would be interesting to see if your conclusions differed when that cutoff has a very specific biological reason for that being there. If that makes biological, that's not the right word. Herbological? Agricultural? Anyway. All right, I think this will be the final question. How are we doing on time? Yeah, I think this is going to be the last question, but not the last time I do this sort of thing, I guess, unless you all hate this. So actually, let me know if you hate this and you think this is dumb, which I really doubt you would. Yeah, let me know if you want me to do more of this. That's probably the better way I should say it. SJRI Gotti, I don't know how to say that. How is a mixed effect model with random slopes and intercepts different from just fitting 3 different linear models, one for each cluster? Hey, that's a timely question because I was just explaining how mixed models work. Theoretically, it's essentially the same. I'm not going to say it's exactly the same, but it's essentially the same. But it's not exactly the same. And so I actually did this when I was a graduate student. My mixed models teacher was a terrible teacher. And so I ended up kind of teaching myself. And there was something that I read in the textbook about this. I didn't even realize that that's essentially what it's doing, is fitting a different regression model to each of the clusters. And there's something in the book that made me think that it might be doing that. And I was like, oh, cool. So what I actually did was I went into R and I literally did that. I fit a regression line for each of the clusters and then averaged them and then computed the fixed effects. And they were not the same. And I looked at the random effects, and the random effects were very different. The fixed effects were close, but weren't the same. It's like, okay, what's the difference? I said, oh, it's probably weighted. Because, of course, if you have one cluster with a larger sample size, you would think that the fixed effect would be closer to that one than another one that has a smaller sample size. And so I did that process again, but this time did a weighted average, and it still wasn't the same, and I couldn't figure out why. And the reason why is because, well, I should say, I think the fixed effects ended up being very similar, like within decimals of the actual fixed effect, but the random effects were different. Why were the random effects different? And the reason why the random effects are not exactly the same as if you fit different regression models is because, it's done simultaneously. So it's fitting all those models at once rather than sequentially like I did, where I fit one cluster and then another cluster and then another cluster. So it's done all at the same time. And the other thing is that those cluster level regression lines are biased towards the fixed effect. So you can actually look at this. If you use FlexPlot and you visualize some of these models, you will see for some of the clusters, like the data points are like way up here, and the regression line is like not even passing through them at all. And it's much closer to the fixed effect. Why is that? Because it's going to bias that regression line toward the fixed effect, if that makes sense. So very good question. And I like this question a lot because it helps us get an understanding of exactly what mixed models are doing. And it shows that you understand what I'm saying, which is great. Like, you understand the basic idea behind mixed models, but it's not exactly the same. Because again, it's biasing and it's estimating all those things simultaneously. Anyway, so that's all I've got to say about that. Hope you've enjoyed it. Don't know why I slipped into an accent just now. If you want more like this, if you want to have your questions guaranteed to be answered, then please come to office hours in December. And I'm only doing it for 3 weeks instead of 4 weeks, so it's cheaper than the normal price. And last class that did it, it was awesome. They loved it. I'd say every person in every class, I got to answer like 4 or 5 questions per person per class. So you have plenty of opportunities to get your questions answered. So if you're interested, please visit the link in the description to Simplistics, where you can sign up for office hours. And if you want to learn more about mixed models, I've also got a January mixed models class that I'd love to see you there for. So anyway, that's all I got for today. So peace out.